Yeah, as noted, I'm Valerie Woolard. I'm a principal software engineer at Heroku. And this talk is Fake Minds Think Alike, AI, Ruby, and Similarity Search. This is a fun illustration here that I made with ChatGPT. You can see if you can spot how many weird things are in it. We've got some questionable wiring here. We've got 2 monitors, 2 keyboards, and 4 people sitting at a desk. It's it's pretty typical of AI art in that it's kind of looks right at first glance, and the harder you think about it, the less it makes sense. So I've got my socials linked at the bottom of each slide. If I'm honest, I don't post that much anymore, but if you write nice things about me or this talk, I'll read them. So there's that. So I'll start with a quick intro. As we went over before, I'm Valerie. I was on the data infrastructure team at Heroku for a long time, doing like automated database stuff for our managed primarily Postgres fleet, but also Valkey and Kafka. I'm now on our AI team, so I do various things around like how can we make AI make developers' experiences better. I'm a principal software engineer. I studied cognitive science and computational modeling of cognition in school, which was a while ago. So a lot has changed since I learned those things. The state of the art in AI is really different than it was 15 years ago, turns out. In my time on the Heroku data team, I led the project to add PG Vector to Heroku Postgres, which is the vector data type that we'll be spending some time talking about. And I am a mom of a toddler. I have a 20-month-old, and I'm about to have another baby. I'm due in a little under 6 weeks. So that's exciting and fun. So the most notable project of my past few years is that I grew a person in my body. This is me and my husband and my baby Remy. This is from about a year ago. This talk is from Brighton Ruby. So this was taken a few days before the conference at Buckingham Palace. I had a lot of fun going around the UK with Remy in this little backpack. It was a good time. Okay, now that we've done the pleasantries, let's get down to business. This talk is about artificial intelligence, AI. I'm sure you've heard the phrase. I'm sure you have heard lots of very strong opinions about it. And so let's dive into what exactly is AI. It's a lot of things. AI is used to refer to applications of machine learning, game theory, natural language processing, Bayesian networks, computer vision, neural networks, large language models, and more. But today's talk and a lot of the current discussion of AI, like when you hear people talk about AI, they tend to be talking about large language models and generative AI. Large language models are also called LLMs. Here you can see that LLMs are actually a pretty small part of the broad category of AI. Their basic big idea is that they take huge quantities of unstructured data and render that data into computer legible formats. So they can take a bunch of text and turn it into a bunch of numbers that the computer can then learn to compare to other numbers, is a sort of simplified way of talking about it. In terms of what AI broadly is, the whole practice of AI, of artificial intelligence, of machine learning, of all of those kind of sub categories is making computers learn, reason, and think, as it were, like or better than human brains. So that's includes things like, let's make a computer that's really good at chess, which computers are really good at chess now. They weren't always, but that's something that we kind of take for granted, that like, oh, computers can play chess really well. And I don't think we even think about that as artificial intelligence anymore. But when it was first being innovated, that's kind of the umbrella that it fell under. Okay, so the problem with making computers act like brains is that human brains are actually not that much like computers, as far as we can tell. There are plenty of tasks that computers are much better at than human brains, and others that they are much worse at. Computers don't actually behave much like human brains. Brains aren't closed controlled systems like computers are. You can't expect the same result given a fixed input from a brain, where you hopefully can from a computer under most circumstances. Brains are living, changing, wet organs. They're very much life forms rather than a black box where the same thing comes in and the same thing comes out every time. Artificial intelligence has been created by humans in part to avoid some elements of human bias and fallibility, but those biases will exist in training data too, and therefore the models that result. LLMs will also sometimes hallucinate and create content that is not supported by training data, and that they can't be relied upon to create logically sound or factually accurate output. I think the best analogy for what LLMs do in terms of generative AI is like a very advanced autocomplete, where they're not actually thinking, but they are very good at figuring out what a reasonable next thing to say is. And you should think about that as you're using them in your work. There are also plenty of controversies around the use of AI and reasons that folks might be reluctant to use it, even in cases where it is or could be a helpful tool. There's no accountability for times when AI makes a mistake. I've included this slide from a famous IBM presentation from 1979 that says a computer can never be held accountable. Therefore, a computer must never make a management decision. Using AI as a substitute for your own thinking, reasoning, or managing is a mistake. And if your AI code assistant ships a bug, you shipped a bug. There's also a concern around the environmental impact of using AI. Large amounts of resources go particularly into the training of these large language models. And then there's the issue of intellectual property. Many of these models were trained on copyrighted or otherwise protected data without the rights holder's consent. And not everyone wants the content they create used to train AI models. There are also plenty of claims for what jobs AI could replace that tend to make people nervous or feel threatened, like marketing, software engineering, lawyers, etc. In a lot of cases, companies have laid off human beings and replaced them with chatbots. Lots of people use AI to do things that they really shouldn't, like draft legal documents, because they don't understand how it works. So this is what's called the Gartner hype cycle. And I found it really interesting in the context of the current AI environment, where when there's a new innovation, there's the innovation trigger. People get really excited about it. There's this peak of inflated expectations where everyone thinks this, or lots of people think that this new technology can solve all of their problems. And there's success stories. There are all of these claims of what this could potentially do, but there's failures as well. Some companies may take action, some may move really quickly and try to capture this hype, and many do not. After that, we have stage 3, which is the trough of disillusionment, where interest wanes as experiments and implementations fail to deliver on those promises. I think you can make lots of arguments for where we are in the current generative AI hype cycle. I think stage 3 feels about right for what we're currently seeing in the market. I think last year we saw a bunch of companies get really excited about AI and all of the things that it could do and how much more productive that we were going to be. And I think that's a lot of those things have proved not to be the case. But at the same time, I think there are kernels of opportunity where there are things that I think AI can be really helpful for, like AI coding assistance. And I think a big part of using AI or any other new technology that's going through a hype cycle like this is to remain skeptical, but also open to what it can do for you. So let's talk about AI. There are lots of new tools in the generative AI category that create new things. These are trained on vast quantities of data. We talked about large language models. Vectors are the actual data type that are the building blocks of LLMs. They are the computer legible representations of human legible data. And AI can be very good at pattern matching, but it is not creative or logical. This is just a fun illustration of how AI can pattern match. This is one of my favorite emojis, the man in business suit levitating. And I was able to give ChatGPT a picture of myself and make a Valerie in business suit levitating, which I think is kind of fun. So next, we're going to dive into some code examples and learn a bit more about how these LLMs work and how they can be used to build something like a similarity search. So I mentioned vectors a few times already in this talk. They are numerical representations of complex data. They're necessary for generative AI, but not all uses of vectors in AI are generative AI. You'll also find vectors in linear algebra, if you've done that. Sentiment analysis, similarity search, image classifications are other examples of AI applications for vectors. Vectors are I find them hard to really work with by hand and reason about. I mostly leave it to the computers. But they can be expressed as a list of numbers, which you can think of as a quantity in n-dimensional space. So they look kind of like, when you are graphing things and it's like an x coordinate and a y coordinate, but there's 300 of them to represent a like n-dimensional space. And they're also not points. They are like, they represent magnitude. So I don't know. I find that kind of hard to wrap my head around, but it's not really necessary to understand on a super deep level in order to work with vectors and understand how they're powerful. And the big idea is that similar things should be close to each other in vector space. So here's a really simplified illustration of what word vectors across 7 dimensions might look like. So these are like example qualities that each number might represent. And then each word vector has some score to represent how closely or not closely it's affiliated with that quality. Note that man and woman in this example are roughly the same distance apart across the same dimensions as king and queen. So here's an illustration of how you might use vectors with your own data. You'd start with your own unstructured data, such as text written in normal prose. You'd feed that data into an embedding model, and that model will output an embedding, which is vector, like what we saw in the last slide, but probably much longer. Most of them will output like a 100 dimensional or a 384 dimension. The number of dimensions kind of just represents the complexity of the model. So it is hopefully the case that higher dimensional models are going to be more accurate. That may not always be the case depending on how good the training data is. So one example of a model you can use is Hugging Face's sentence transformers. That's actually free to use. You can just set up an account on Hugging Face and play around with it. It's pretty fun. One of OpenAI's embedding models, or one that you train yourself. And the embedding that results is a vector generated by the model, and your model will output a vector of a fixed length. So when you build a similarity search, if you're trying to find things that are close together, you're going to want to create embeddings for those things, whether those things are words or sentences or images or articles. All of these types of things can be fed into an LLM to give you vectors. The different models are going to be better optimized for different types of things and for different lengths of things. There are some that are meant only for individual words, some that perform better on longer data, like paragraphs or pages of data, that kind of thing. And then when you want to find similar things, you perform a nearest neighbors search. So you can use, the distance formula that you've probably come across at some point in your studies. You can use other distance calculations. There are articles out there around what distance calculation is going to work best for different kinds of data. We're not going to get into that in this talk, but if that's something that's interesting to you, definitely look into it. Tools like pgvector are going to have different distance calculators like kind of already built into them. So you don't have to like actually manually do the math. You can just decide which kind of distance you want to use. Now let's get into code. Ruby is not the most popular choice for building AI applications. A lot of folks use Python, but I can use any type of gem to control any type of snake. There's also a lot of, you can just use HTTP if you really want to get down to it. But I would say if you're trying to spin something up like really easily and quickly, Python is probably the most straightforward language to use, but we'll go through some of the Ruby tools that are available. Okay, so this is just kind of word salad about some of the tools that are in the world that you can use. There's Pinecone, which is a straight vector database. It only stores vectors. You can use Postgres and pgvector. So this is your standard SQL database, and pgvector is an extension that adds support for vector types. I find this really helpful because you can also write your normal database queries and couple those with some of these like nearest neighbor searches. So that, I think that's a really powerful application to have that data living beside each other and sort of queryable in tandem. And then if you're just trying to demo something really simple, there's always SQLite and SQLite Vec. In terms of Ruby gems that support some of these things, there's pgvector, there's Neighbor, there's an OpenAI Ruby gem, and there's one called Informers. So some of the considerations that you'd want to take into account when you're deciding what data to send to these embeddings, to vectorize, as it were, and what model to use, are how that model was trained. Sentence transformers, which is what I've used for some of these code examples, was trained on Yahoo Answers, Reddit, Stack Exchange, Wikipedia, WikiHow, and other internet content. A model that was trained on data that is closest to your use case is going to be what performs best. So if you're doing, you know, medical analysis, like maybe you don't want to use a data set that was trained on Reddit and Yahoo Answers, but that's up to you. So let's just say I have a huge list of books that I want to read saved in my database, along with their descriptions. And I'd like to find a new book to read. So what I've done is I've added embeddings for each of the book descriptions. And I would like to have my artificial intelligence tell me what book I should read next. So I'm going to say, I'm interested in reading a quirky, magical, realist fable. So I'm going to embed that, like, that sentence. And then I'm going to find the nearest neighbors in terms of what book description most closely fits that, you know, my stated desire of what I want to read. And using Euclidean distance. And then pull out the title of that book from my database. The title that it suggests is The House in the Cerulean Sea. And let's see how well that performed. Does that actually fit the bill for a quirky magical realist fable, like I asked? The actual English description is a thoroughly enchanting novel that follows lovable Arthur, the caretaker of a magical misfit orphans from around the world, full of whimsy, romance, and a touch of intrigue. The House in the Cerulean Sea will make you smile from the first word to the last. So that actually does feel like it did a good job of finding something that matched the interests that I gave it. But what if I wanted a more personal touch? What if I didn't just want it to give me the title of a book? What if I wanted it to write a more human-friendly explanation of why I should read this book? That could use a strategy called retrieval augmented generation, which is often called RAG. It uses generative AI prompts plus relevant documents from a user query. So an illustration of how that might work. So here's a flowchart from Wikipedia on how to construct a RAG query. Basically, you're giving the LLM a bit more relevant context in the prompts to generate a better response for you. So an example of what a prompt might look like is I'm looking for interests for my next read. Tell me why I might like, here I'd perform the nearest neighbors search and get that House in the Cerulean Sea book title. And here is the description. So basically feeding all of this information back to the LLM to have it write a recommendation for why I should read this book. Some models have bigger context windows, and you could potentially put way more information into your RAG prompt. So I could feed the prompt more information about books that I like, or descriptions of other books that I have, or reviews by other people of books I might be interested in, to make it more intelligent, as it were. Some other implementation ideas that you could use with a lot of these same concepts are finding related articles in text, allowing people to search content with natural language, categorizing images. All of these examples we've talked about are actually like finding similar things, but by the same token, you can find really dissimilar things. So you could find the things that are most unlike something. And I'm hoping this has given you one practical potential application for vector search and AI. And I'd be interested if you have other potential ideas. And that's it for my talk, but I'd be happy to answer any questions that folks have.